In this video, I wanted to look at the composition of two polynomial functions. And I talked about this a little bit in class, but recall that f circle g, this does not mean product, this means f of g, and how we define that, which again you can find in your book or a number of other places, is defined to be this. F of g of x is defined to be f parenthesis g of x. Or another way of saying that you're going to take one function and plug it into the other. And g of f of x is defined to be g parenthesis f of x. In order to actually solve this, the idea is works by substitution, because g of x, we know what that is. You know, we need to obviously know what both f and g are. And in this case, let's use our same examples. G of x is x minus 5. So let me just go ahead and underline that in green, just because this will be, one of my functions. And the idea is I'm going to substitute that function into f of x, because that's exactly what it's saying. I'm changing my domain from just x, the generic variable, to an entire function. And if I substitute that in there, this would be equal to f of g of x. Well, g of x was just x minus 5. So that's just another way of saying I'm going to take x minus 5 and plug it all on in. And from here, again, we know, well, what is f of x? F of x was x squared minus 2x plus 7. I'm going to change the entire input to x minus 5. Because, well, what f of x would do is square the input, then minus 2 times the input, then plus 7. Because normally we are just plugging in a number or x or whatever, but if we're plugging in an entire algebraic expression, we want to make sure the entire thing goes in there. So, this is typically a little bit trickier to understand. So if I'm kind of losing you on what I'm doing, basically I'm replacing each x in f with the entire g function. And so I'm kind of imagining taking that guy and I'm jamming it in there and there. And every single x will need to be replaced by g, because that's exactly what this means. F of g means I'm plugging the entire g into f instead of just a number. But basically, now to figure out what this is, I have to use my rules of algebra, because x minus 5 squared, this means, well, x minus 5 times x minus 5. And I want to make sure that I don't mess that up. And then with negative 2 times x minus 5, again, I would need to use the distributive property there. So that would be negative 2x plus 10 plus 7. And I'm going to go ahead and make sure to FOIL out the x minus 5 squared. And there's actually a shortcut for squaring binomials like this, which I didn't have time to talk about in class this week. But the shortcut is, if you want to square something, you can always take the first thing, x squared, and square it. And because we're going to do, if we're foiling, notice we would then get minus 5x and another minus 5x. Since it's exactly duplicated, because when you're squaring, that will always be duplicated, that's always going to double the inner products. Or in the FOIL process, we have the outside and the inside. The outside and the inside should be exactly the same, right? Negative 5x and negative 5x. Well, if I add those together, that would be negative 10x. And that's the shortcut. So if you ever hear me reference this shortcut, basically what you do is you start with x, square this, multiply these together times 2, and then you square this, because that would be the last product here, right? Plus minus 5 times minus 5 is plus 25. And that would be my full FOIL. And just to sort of go over the shortcut one more time, square this, multiply these together times 2, square that, and that would leave me with x squared plus minus, because you're going to do minus x times plus x times minus 5 times 2, which would be negative 10x, and then plus 25. But, I don't generally recommend students use that shortcut unless you really, get it. And I would always recommend just writing it out and foiling it all out. And I can't forget I had all this other stuff to also contend with. And then, of course, I can combine like terms. So I'm going to end up with x squared minus 12x plus 35 plus 7 is plus 42, the meaning of life. And anyways, after all is said and done, what I'm going to get is f of g of x, which is again, different. Notice that this is not the same thing as f times g. It's very different because f times g of x represents taking an entire function and multiplying it together. F of g represents a function actually being plugged into the other. And actually, I wanted to talk about like how can you differentiate the meaning behind this in just a minute by using like the metaphor of the function machine. I wanted to talk a little bit about the idea of why these are important and why this meaning of composition is, well, first of all, different and needed for a lot of other math. But before I do that, let's also reverse it and see what happens. So let's see what happens if I did g of f of x. But also to sort of summarize, we finished solving f of g of x, and that's, again, a whole new function way of joining them together. G of f of x, though, is notably different. Like multiplication is commutative, it will be the same regardless of what order I do it in. But if I did g of f of x, it's not the same thing as f of g of x, and let's just see why. So here, in the same exact line of thinking, I'm going to be plugging f of x into g of x because that's on the inside here. And f of x, again, going back up to my top of the page here, was given to be x squared minus 2x plus 7. And so in the same way, I'm going to be basically taking the entire f function, plugging that into g. And what I like to do is replace my input of g with the entire f function by just substituting. So that was x squared minus 2x plus 7. And that is going to be the entire input. And now again, the meaning is similar where I want to take the entire f function, and this is now going to go into g. Before I plug g into f, here I'm plugging f into g. And g is x minus 5. So in order to solve g of x squared minus 2x plus 7, which is what I have written right here, well, usually g is x minus 5. But here I'm going to be replacing x with the entire function. So again, I could kind of think of that as, well, parentheses, the input minus 5. And I'll put a little bit more room here, because that's what g does. You take the input, take away 5. And here the input is just a lot more, because I'm plugging in the entire f of x into g. Or again, you can think of it as replacing x in g with f of x, the entire function. But that's going to leave me with x squared minus 2x plus 7 minus 5, and that's actually a lot easier. That would just be x squared minus 2x, because there are no like terms, and then 7 minus 5 is just plus 2. And this would leave me with g of f of x, which again is notably different than f of g, and it's different than f times g, f plus g, and f minus g. They're all different as well. So to wrap up now, I wanted to kind of talk about why do I care about all this stuff, right? There's all these different ways we could combine functions. Why are they important? Well, first of all, just being able to do math on stuff is important, right? If I have mathematical objects, I'm going to need to know how to add, subtract, multiply, and divide. That's just a key component of math in general, and especially algebra. But I like to use the function machine metaphor to try to think about what these sorts of things are doing. And like kind of what I mean by the function machine, this is probably something you've heard your teachers use as a metaphor before, but basically I could imagine a function f as a machine where it takes the input x, some number or some algebraic expression, it grinds it through the function, and out from that comes the range, which we call f of x. Like, I start with a 5 and out of the function comes 2 or something. And domain is going in and range is coming out. And f is just like a mathematical calculation which figures out the outcome. And kind of taking it back to there's the correspondence between input and output, domain and range. Just like in 2010 the Giants won the World Series. The function is what calculates and finds out our answer, especially on the mathematical side. Well, if I wanted to know what is f plus g, well, if I'm taking two different functions, f and g, they're entirely different things, and if I ran f x through g, what I would get out of it is g of x. And the f plus g of x would be the literal combination of just taking whatever f does and whatever g does and combining them together into a single function. So I could kind of imagine f plus g of x being 2 and 1, where it's a combination of them. Or, the same goes for subtraction, multiplication, and division. It's just a different algebraic combination of those things. So what's different, though, is function composition. Function composition is a little bit different because instead of just taking the functions and adding them, subtracting, multiplying, dividing, we're actually going to be chaining them together in succession. And that's kind of the idea of what the open circle f of g of x means, which again we call composing them. But like, instead of doing them separately and adding them together, let's say that I first ran x through f of x, and then I took the result of f and I plugged that into the g function. And then what came out of g would be g of f of x. And notice this would be g of f of x, or we would again call this the composition g circle f function, because first I plugged x into f of x. And right, when you're doing functions, it's kind of backwards because we write f of x, it's not from left to right, it's from right to left, because like the input is over here, the output is to the left. And then the answer, f of x, is actually going to be used as the domain of g, or the input into g. And what would come out is g of whatever I sent in. So in a particular chain, by running a number through f, then through g, that is what we're doing when we're composing functions. We're running it through them in succession. And it kind of can, well, it's not necessarily important, but it's nice to remember that actually g circle f, we're actually plugging into f first. Because if we kind of think about, this, what I have is f of x here. If I imagine, say, plugging 2 into the composition, I would start on the inside and work my way out. And that's the general rule for how we deal with parentheses in math, right? Anyways, is you want to start with the innermost parentheses and work your way out, which is another reason the notation kind of makes sense. And basically, it's like a combined function which would run them through each other in succession, and the composition function is like doing 2 and 1 in a particular order. But it's not the same as multiplying, adding. That's just kind of different. And one of the uses of function composition, in computer programming particularly, you can kind of imagine a function as a computer code, which when you plug something into the code, it's gonna do something and give you a particular result. And you can use computer codes to do math, but you can use them to do other stuff as well. And sometimes you want to run a particular code and then run another code after. Well, kind of the idea of the function composition is it's doing 2 and 1 in the order that you want. And again, in this particular case, we've kind of simplified the result where, we did the algebra and figured out what would be the net result of that chain, which is kind of simpler than doing one then the other and kind of putting it in order. And the same thing for, this would be g circle f in this particular case. F circle g would be the same idea, but it would instead be, plugging into g first, then f. And that would give us, the other composition. Anyways, I'm rambling. Let's try to wrap this video up. But function composition is just the main thing to know is it is different than multiplying. It has a particular meaning, and I recommend, following this sort of strategy for figuring out what it actually is. But hopefully that kind of helped with understanding what's the point of a function composition. It's just basically running the two in succession. And often we refer to these as function chains. Like in calculus, you have what's called the chain rule, and those sorts of rules are often referring to functions within another function. And it can it's kind of an important thing in math, because sometimes we have a polynomial within another function and we want to know, well, what's going on and how are they put together. Anyways, that is it for this chapter. And the test will will run from chapters 1 to 4, and chapter 5 will not be on the test. So this is kind of it. This is the end of the discussion for now, and we'll pick back up with algebra, polynomials, and factoring when we start chapter 5.